let's begin our workshop. Our first talk is by Professor Alan Yuille. Alan Yuille is a Bloomberg Distinguished Professor at Johns Hopkins University with appointment in both Cognitive Science Department and Computer Science Department. Dr. Yuille completed his PhD degree at Cambridge University, supervised by Stephen Hawking. His computer vision research has been widely recognized and cited, winning several prizes, including Mar Prize. The title of this talk is Defending Against Random Occluder Attacks. Hi, Alan. You can share your screen now, and the floor is yours. Let me first turn off my.
Okay, so I'm on. This will stop other screen sharing. Yes, I guess that's okay. And I think, can you see my screen?
Oh yeah, we can see your screen now.
Okay, so yeah, well, thank Chihang and the other members of the committee for inviting me to speak. I guess people give me feedback if I'm not talking loud enough or possibly talking too loudly. So the title is Defending Against Random Occluder Attacks, but actually a lot of my talk is going to put this in some degree of context. So the plan of the talk, part one will be brief history of performance evaluation, the infinite space of images, and perceptible adversaries. Part two, infinite space of images, yet again, domain transfer and combinatorial complexity. And then part three will be on random occlusions and defending against them. And I guess the main point of my talk, which I think probably many people in this audience would agree, is that adversarial attacks are critical for dealing with the infinite space and the combinatorial complexity of real world images. So when adversary attacks started, I thought maybe there was sort of like a small fringe area that would never happen. But the more I thought of it, the more I thought that they were really critically important for vision. And if you don't already agree, I hope I'll persuade you about that during the talk. So here's part one. This gives a bit of history. So brief, so when computer vision started in the late 1970s and early 80s, conferences, CVPR founded, all the other conferences came on a little bit later. If you worked in the subject, you were happy if your algorithm worked on a few synthetic images. And that was enough to get your papers published. However, then reviewers got a little bit tougher in the late 80s, and you now had to show that your algorithm worked on a few real images before they would publish it. Okay, then for most of the audience, maybe all of them, then benchmark data sets were created in the late 1990s and early 2000s. And this led to the standard paradigm where you have balanced finite size test and trained data sets plus some validation set. And so this was backed up by some nice sort of mathematics, probably approximately correct theory and so on, and general thoughts in computer vision. But is this right? Is this the way we should be evaluating algorithms? Has history of performance evaluated ended, like the historian Francis Fukuyama suggested in 1992? And I'd suggest no, that like that historian, history has not ended at all. It's changed. And that in computer vision, we should move to a new phase where we try and test our algorithms by adversarial attacks and test on infinite data sets while only training on a few images. So infinite space of images, so images, infinite space, you have a training set, you have a test set, finite size. Is that enough? Well, I think even 15 years ago, 20 years ago, there was some realization that this wasn't enough. And I'll mention the idea of hard negative mining. And again, to give a little bit of history, by the late 1990s, AI systems could defeat Kasparov at chess, but computer vision researchers couldn't detect objects in images, which was rather embarrassing. But in the year 2000, Paul Viola gave a live demo of face recognition at NIPS, or neural NIPS, and how Well, Paul used machine learning algorithms, cascades of Ada boost, which were trained with positive and negative examples, but that was not enough. You also needed hard negative mining. The point being that the set of positive examples was big enough because faces don't really vary very much. Your set of negative examples was not. If you wanted to detect faces in real images, your set of negative examples had to be big enough to include the near misses, image patches that occur in real images that look like faces but aren't. So hard negative mining, augment your set of false negatives by including false positives you get, and keep growing your data set by having more and more, by carrying on doing hard negative mining. For myself, I experienced this on work in text detection, which we're working on to help the visually impaired. And having seen Yuille's talk, I realized that the methods he used were very useful for text detection. And so we could train and test, and we had a paper in CVPR 2005 about doing this. But really, to get it to work so that you could walk down, walk through New York City, top right, and have some system that would find text in real time, you couldn't just rely on a fixed size annotated data set. You had to make your set larger and larger and larger. So you use hard negative mining to find near misses. Here are a few of them for text, things that might be text if you don't look too closely, and also hard positive mining to reduce false negatives. So you really had to keep growing the data set by working on real images and seeing where it broke down. Now, a general point which comes up, and I guess a lot, this perspective will come out in Alexandra Madri's talk if he's discussing this aspect of his work, but data sets really consist of islands in the vast infinite dimensional sea of real images. The space of all images is infinite, so our finite size data sets are only an infinitesimal fraction of the set of images. Now you can address this to some extent by the idea of adversaries, perturbative and imperceptible, which is for me somewhat in the spirit of hard negative mining. And the concepts of the min-max criterion due to Madri and others, in terms of the metaphor, it means that the islands are given territorial waters. Each data point turns into a sphere of radius r, etc. So you are learning to populate this infinite sea, even though you've got a finite set of samples. And so there's a large literature on this aspect, which I won't really address, but here is, I guess, my first point about infinite dimensional space of images and the values of adversaries for exploring it and dealing with it. So now a second point about infinite spaces of images. So data sets for the same visual task can be very different. So one of the earliest data sets in computer vision, annotated, certainly the earliest for edge detection, was the Sowerby data set on the left, which was images of the English countryside, which had roads, but a lot of vegetation. So the background was heavily textured. On the right-hand side, another data set was South Florida. The images were taken indoors. They're very clean. There's no background texture. There's a Berkeley data set for people interested in the history, but that came along after these ones. So edge detection was much more difficult on Sowerby than on South Florida because there was so much background texture. And a standard edge detector like Canny would be terrible on it. It would be finding edges all over the place. So domain transfer, so this led to a domain transfer problem, how to get an edge detector that's trained on Sowerby to work on South Florida and vice versa. And so the first learning-based attempt to do edge detection, which was due to Scott Kanishi, a student of mine who was at Berkeley, was by chance also possibly the first to perform domain transfer, to the best of my knowledge. And I really like it if anyone knows anything else, because any other earlier example. His detector was able to do this because of details about how he went about it. He was trying to learn distributions for features, image features on edges and in the background. and then he could use log likelihood ratio tests to classify and to do edge detection, effective on both data sets. But he was also able to do transfer. Okay, why? The key idea was that there was a target you were trying to find, which were the edges, and the statistics for the feature responses were fairly similar on both data sets, because edges are edges. The statistics of the background were very different, because Salby had a lot of texture and South Florida did not. On the other hand, most of images are not edges. So if you want to estimate the background, you can do it without any annotation. You just do the statistics on everything in the image. It's a bit contaminated, it doesn't matter. So it struck me as domain transfer became hot again that in fact, we had actually published a paper on it, or Konishi had published a paper on it 15, 20 years ago. But it's an important problem, remains a really extremely important problem, I believe. So different data sets to get another type of metaphor, for the imperturbable, the original adversaries, non-perturbative ones, you have the metaphor of islands in a vast infinite dimensional sea. And for different domains, you've got a tribal metaphor. You have a large number of isolated tribes separated by mountain ranges and jungle with different languages and customs. So take Papua New Guinea, which is slightly larger than California. There are at least 312 tribes and 832 languages. So will findings on one tribe generalize to other tribes? Well, you don't know. You have to do the experiments and find it. And this is really important in practice, not only in sort of computer vision or natural images, but for computer tomography. Different hospitals take CT scans using different types of scanners, different protocols for different purposes. So you've really got a whole tribal set of different data sets, and do algorithms that work on one data set taken by JHU Hospital in the radiology department, work on data sets taken in the Harvard Medical School? The answer is often not, because the domains are different and transfer has to happen. So, what's happening here really is that, again, with this infinite sea of images, within it, there are sort of different oceans, sub-oceans, which are the different domains, and we need to deal with those as well as dealing with the individual seas themselves. Here's domain transfer again. Here is images of horses. You want to do pose detection. Here is two computer graphics images of horses. Here are line drawings of horses. Here is pop art of horses. Here's real images of horses. We want to have algorithms that will not just work on the real images, they'll work on the pop art, they'll work on the line drawings, they'll work on the computer graphics. And there's a paper by Jiting Liu about this. There's a literature on this, and there's a recent work on that, which I might mention if you're interested. So now, data sets. Now the third point about them is also exponentially and combinatorially large. So is any data set big enough to be representative of the real world? How many images should a data set have? People ask me questions about that, and my honest answer is I say, I don't really know. You have to make a data set, then you have to try to generalize it, etc. But here is a thought experiment from a paper we did a few years ago. Suppose the images are generated by a computer graphics model, I'll show in the next slide, and the image from computer graphics, it's caused by several factors: the geometry of the object, the texture and material properties of the object, the lighting conditions, and also, to some extent, the background surrounding the object. And so a quick study shows that you get an exponentially sized data set just for a single object. So any finite sized data set represents only an infinitesimal fraction of reality. And so great performance on any fixed data set like ImageNet does not guarantee good performance faced with the complexity of the real world. And to go back to quote Shakespeare, you know, I could be bounded in a nutshell and count myself king of infinite space. Within my nutshell, localized nutshell, everything works well, but does it work outside the nutshell? I don't know. So here is just the illustration of that, images from synthetic computer graphics models, lighting, you know, viewpoint, and here for this thought experiment, there were 4 parameters, lighting, 4 parameters for this, light sources, type, etc., texture, only one type of texture, only one type of material, scene layout, okay, 3 variables, total of 13 variables generating the image. And so you allow 10 to the 3 possibilities for each parameter listed. Well, you get 10 to the 39. And so this is just for a single object with background. And this obviously is a data set that's completely impossible for us to have at the moment, and even in the conceivable future. And this is for one object only. Of course, many of the images in this thought experiment are going to look so similar that you can probably reduce the amount, but still this isn't intended to sort of make you think about that. Okay, data sets are combinatorially large. Well, that situation becomes even worse if you have multiple objects in a visual scene. You can generate a visual scene by selecting objects from the set of all possible objects, which is estimated at being 20,000. You place them in random positions. This easily gives you a combinatorial number of images. So, and suppose you just, you know, you reduce this and just consider occlusion alone, the same argument goes through. You can occlude any object in a combinatorial number of ways. And here are some examples that I think Xiang created. You know, you occlude the penguin with a television set. The deep network, at least the deep network at that time, thinks that the penguin is now a human. You occlude the monkey with a guitar. The deep network, at least at that time we did it, thinks that the monkey is a human. And thinks the guitar is a bird. So large number of ways of doing, of including objects, and from these types of experiments, they can certainly affect the deep network. So occlusion, and maybe people don't think about this, I would say is also a type of attack. There are infinitesimal perturbation attacks, the standard type of attack that came up. There are patch attacks, which we'll hear more about by other speakers in the in this meeting. But I think there's also occluders, somewhat similar to patches, should be considered a type of attack, and there's a great deal of them, and they happen in many world situations, even if they don't happen very much in benchmark data sets. Okay, so this raises me, you know, and I guess others to think of, you know, what does this mean? You know, current ways that we evaluate and, you know, train and evaluate algorithms are based on finite size data sets which are balanced. But if the world is combinatorially large, infinite sets of images, infinite, you know, large numbers of different domains, combinatorial numbers of possibilities, can any finite size data set be big enough to adequately test your algorithm? And also, as computer vision gets a bit more ambitious, shouldn't we start worrying about the worst case rather than the average case? Our performance at the moment, you know, is generally based on random sampling. So we're calculating, you know, performance is sort of the expected version. But, you know, you don't want a Tesla to detect pedestrians on average. You want it, you know, to the worst case, but never, you know, always to be able to detect pedestrians. And if you're designing computer algorithms on CT scans to find tumors, you don't want it to be on average good at finding tumors. You want it to be really good. You care about the worst case. So here is just a conception here, just to make people think a little. An adversarial examiner, instead of testing an algorithm by its performance in the random samples of images, which is what we do now, allow an examiner to test a sequence of images where each image is selected based on the algorithm's performance on earlier images. So this allows the examiner to probe the weaknesses of the algorithm, let your worst enemy test it, not by a bunch of random samples. Because I think conceptually, would you really, would a professor test his or her students by asking them a random selected set of questions? No, you wouldn't. You'd ask them to a set of questions where each question depended on their answer to earlier questions. Okay, so that's the issue about testing. How should you test? You need to be able to potentially test on an infinite set of images chosen adversarially. Okay, now if your data sets are combinatorially large, then you run into another problem, which is how to train algorithms. And the answer here is, and this will be the last part of the talk, we should train models that are robust to data sets, which is related to what's now called out of distribution learning. As parenthetically, I'd say it may be sensible to study how human infants learn perception, because this is very different than how human machines learn it. And the human visual system still remains the gold standard for general purpose vision. So now to move on to a concrete example of this, I'll discuss training algorithms on data sets with limited occlusion and testing them on data sets with occlusion. So humans significantly outperform deep nets if you show them images with heavy occlusion. That's been tested. And can you design algorithms which can do better? So here, and I've left myself only a little time to describe it, but this work is in CVPR 2020, a Kortulewski et al. So there's more information about it there. So again, in natural images, occlusions happen all the time. These occlusions could be considered random attacks here because they're not, at least not in the way we're doing it. We're not trying to target the worst case. We're just putting them on at random, but extending them to attacks is a natural thing to do. The occluders, again, highly variable in terms of shape and texture. So you really have exponential complexity. And vision systems must generalize into these exponential complex domains. Deep networks, you can evaluate them on this. They do not do badly when there's a lot of occlusion. This is from COCO data set where you divided it into low occluded, middle occluded, and high occluded. So they don't do very badly on it. And they do, of course, enormously better than anything we had before deep networks, but they're not performing terribly well. You can certainly improve them by training of augmented data, and you get larger amounts. The performance certainly gets higher. On the other hand, as being argued, in principle, the amount of extra data that you'd have to train on might end up by being combinatorially large. So here, think of it from a different perspective. Instead of having a standard deep network that has features and has a top is discriminative, get a model which is generative. So the first part of the deep network is the same, captures features up here, but then at the top, it's got a generative model of the features. And that would be based on an object, the object viewpoint, etc. And then it would be modeling the features, and it would be modeling, and this is important, it would be modeling the spatial patterns. There's a little bit of mathematics here, but I'm putting it up more or less just to show that there is a little bit of mathematics, and that the model here is generative on these features, conditioned on the object, conditioned on the model. So here is perhaps a nicer figure. At the top, class scores would be objects. Then there would be class mixtures, which would correspond to viewpoints. Then there would be feature vectors here, which we used to call visual concepts, which are roughly like part detectors. This model, I should say, is trained in an end-to-end manner. It's not given any supervision about the mixtures or anything like that. So it's given exactly the same information that the deep network has, but the algorithms for learning enable it to estimate these mixtures and so on, these parts, etc., in an unsupervised manner. A little bit of details, math details there, so we'll skim over it. Here is a global overall loss function. You can minimize this. Part of it can be minimized by standard backpropagation. Other parts would be minimized by clustering, because you'll need clustering and so on to get the internal mixtures. Okay. These parts here are going to correspond to parts, roughly. This hasn't been fully quantified, but they would correspond to, here is an engine of an airplane, here are windows, here are the front wheel of a bike. And so the idea is that the models would learn so that for a particular viewpoint, they would expect to find a particular part there in that position. Okay. The mixtures here are bicycles from the side, bicycles with 3 wheels, etc., bikes from different angles. Again, learned unsupervised, not learned directly. And for the occlusion model, now that you've set it up as a generative model, the occlusion is almost trivial. Because the generative model is going to say that for any viewpoint, any object, any viewpoint, you have a distribution of the feature vectors at particular places on the object. Okay, you're going to have features for tires in the front right of the car, if you see it from the side, features for windows in other parts of the car. Okay, so you can predict what feature vectors you are going to have if the car is there from that viewpoint, or the bicycle, or whatever you're looking at. Now, if you find that some of those features are there in the right positions and a few are not, you then decide that the few are not are probably occluders. So what you do is you extend your generative model so it's not just generating the feature vectors, but it allows the possibility that the feature vectors at a particular position are generated by a random process that generates something which is not on the object. Okay, so here is mathematics of that, fairly simple. You know, so it generates something of what the object does not look like, so you can just get that by taking a random set of images. Okay, then, so now generative model allowing certain features to a particular position, you know, at different positions to be generated by some other process. So if you've got an image like this of the car, the algorithm is able to first say that it's a car, say the viewpoint of it, but is also able to say that this tree here where my mouse is moving, well, that's not the features it expects to find from a car seen from the side. So it decides that they're occluders. They're generated by this alternative occluder model. Similar for this vertical bar here. This is not what the model expects. So it switches over and says the occluder should explain it. And then this model of the image of the face of the human again. So the generative model generates the features. You're explaining why certain features are missing because of occluders, which means that as well as having some robustness to occluders, you've also got the ability to localize them to find where the outlier model switches on. There's a competition between the object model that's generating the features and the occluder model. Here called the outlier model. So here's quantitative evaluation of it. You can do this, you can put that in, and then you can sort of get graphs and numbers like that, which are all nice. But so far, I think I've given you the main idea. Okay, now you can then see how well do we classify these vehicles. It's only working here on vehicles, has been extended to other models since then. And so here, VGG, ResNet results are not so good. As you put this in here, you use these comp nets, which are generative on the feature vectors. You do a lot better and you get far higher results, even under fairly occluded positions, fairly occluded objects, as well as being able to estimate them. They can be applied also to object detection. There's another thing about that, and there's some interesting aspects of that. But again, the idea is you're generating it. You want to be robust to occluders. You want to be robust to context. Okay, so that's a rather fast overview of the technical work. But here is the conclusion. First, that adversarial attacks, I think, are not just sort of fringe interest. They're critical for dealing with the infinite space and the combinatorial complexity of real-world images. The space of images is infinite. You know, there are a number of metaphors, they're islands in the vast infinite dimensional sea. There are also different image domains, analogous to different tribes with different languages, and domain transfer is critical, as well as dealing with perturbative adversaries. Then the space of images is combinatorially large. If you think of how images are generated from computer graphics, no realistic data set can capture this complexity. Maybe we need to rethink the standard paradigm for testing it, possibly look towards adversarial examiners that try and target weaknesses rather than random samples. And finally, perhaps we need to develop new algorithms. And I've shown you one example, CompNets, which can be trained on one data set but can generalize to another. And I think we'll also have other talks about that later. So that's the end of the talk, and I'll stop now. So thank you very much for your attention.
Hey, Alice, thanks for your talk. Yeah.
Okay, I'll mute myself now.
Okay.